Okay, so at the end of high school, I enrolled here, University of Melbourne. I was doing arts degree, a science degree, diploma of music. And this was because at high school, I liked English, I liked mathematics, and I liked playing the piano. So this combination allowed me to do those three things. If you look at this and you're thinking, well, this is somebody who has no idea what he wants to do, you're pretty much right. And it turned out that for me, the most important things I did were actually things that I didn't know about at the start of the university. So I did philosophy, and the parts of philosophy related to logic and philosophy of mind were the parts that I liked the best. And this book, Gödel, Escher, Bach, I think was one of the reasons I got interested in philosophy. I read that in high school and thought it was cool. I got interested in computer science. So that photo on my title screen was a bit misleading. I was not the kind of kid who liked programming from an early age. I only got into programming at university. And that was partly as a result of reading this book here. This book, Hackers, Heroes of the Computer Revolution. And it was the social element of computer science that really appealed to me. The idea that you had this group of people and they were playing with ideas and building new things. I just really liked that. And I was glad that this book led me to take some computer science classes. Psychology came later for me, maybe about halfway through my undergrad degree, maybe slightly later. And I still remember the reason I signed up for my first psychology class. This book by Frank Salloway had just been published, I think. I hadn't read this book, unlike the other two here, but maybe I'd read an article about it in the news. And it talked about birth order theory, the idea that where you lie in your family, among your siblings, has a major influence on your personality and your career and things like that. So the idea is that older children, maybe they're more confident, outgoing, driven, they achieve more. Younger children, more creative, and so on. So maybe I was interested in this theory because as a middle child, maybe I felt neglected. I'm not sure. But I remember I was never terribly convinced by the evidence that I read relating to this theory. And I think some later studies suggested that Salloway's evidence doesn't hold up all that well. But what really struck me was this seemed like a really big question. You know, does the position, your birth order position in your family affect the person you end up turning into? And it struck me, I was really struck by the fact that psychologists hadn't figured this out. So it seemed clear. Here was a field where there were really big questions that were unanswered, and I wanted to learn more about it. So I did these things and later got interested in cognitive science, particularly by reading books by Steven Pinker and other popular science writers and scientists. Through all this time, though, I don't remember having a clear idea that I wanted to go on and try to do a PhD and do research. In fact, I remember feeling that I didn't really have the ability to do research and come up with new ideas. And I'm not sure why this was exactly. I think maybe it was partly Australian culture, growing up feeling that all of the important stuff is happening somewhere else. And, you know, maybe here you can learn about what people are doing at the big centers, but it wasn't kind of clear to me that it was possible to develop your own ideas as a scientist. So if I couldn't do science, maybe I wanted to be a science writer instead. And during my university years, I did actually a course, a correspondence course in journalism. And as part of that, I wrote an article about card counting that I submitted to the Good Weekend. It was rejected, it was never published, but you know, it was a good experience to try to write this thing. I think the single most important factor that led me to apply for a PhD was the group of people I knew coming out of the Math Olympiad training program I mentioned before. A number of them had gone overseas to do PhD to places like Stanford and Caltech and Princeton. And without them, it wouldn't have been clear to me that doing a PhD overseas was even an option. So following their lead, I applied to a number of places. Not all of my applications were successful, but I got offers from a few places, including MIT. And I went back and looked at my application materials to MIT, and here's what I wrote. And this part here, I think, still captures the way I think about cognitive science. It does seem almost too good to be true that there's a field that combines computer science and psychology and philosophy and all the most interesting parts of those fields and puts them together into a single thing. So I remember feeling really excited when I learned about that by reading books by Pinker and others. And I also think it's a case that the university here didn't have a program in cognitive science, so I sort of felt like I was doing this on my own. So that's something that, you know, I aspire to change it. I'd like to have more of a presence for cognitive science here and make that more visible. So I stand by all of these things that I wrote here. The other parts of, some other parts of the application no longer really capture what I think or what I'm interested in. I think at the time, even though I started out being interested in questions like birth order, at some stage I decided that social psychology, high-level cognition, these things were maybe too fuzzy, too hard to actually make progress on as a scientist. And that the place where you could make progress was if you went down to a slightly lower level and you looked at problems like motor control or animal learning or computational neuroscience. So many of my applications to grad school focused on that area. And you can see that reflected in my statement here to MIT. Okay, so despite the fact that I had these examples of successful friends who'd gone on to PhDs overseas, I really didn't know what I was doing entirely. So at some universities, I said I wanted to work with people who were now emeritus, and you know, I just didn't understand the process that well. And at MIT, actually, the person I wanted to work with wasn't that interested in me and what I wanted to do, but I ended up meeting Josh Tenenbaum, who had just taken a job at MIT and wasn't actually there yet officially. He was just there for visiting day, and I really liked what he was doing. He was working on high-level cognition. So he's, I suppose, the one who brought me back to thinking that you could look at high-level cognitive problems in a rigorous way. One of the reasons I think I wanted to keep working on cognitive science and follow the academic track was that thinking about cognitive science was important to me as a way of trying to understand people, trying to understand the human condition more generally. So here's something I wrote in a scholarship application at the time, and I'm talking about the idea that the computational revolution, the fact that now we have digital computers and you can build computational models of the mind, really fundamentally changes the way we think about what minds are and how they work. And I still think that, and despite the fact that when you're actually doing academic research, maybe you spend a lot of time working on specific problems, very detailed problems in a very specific area, these kind of big questions about what the mind is, why it works the way that it does, and how that affects how humans are and what they do. I still get excited about those things. My interest in science writing was still in some of my applications. So here I expressed the aspiration that one day I wanted to write some popular science myself. That hasn't happened. I'm not sure if that's ever going to happen. But yeah, I guess the fact that we didn't have a cognitive science program here at Melbourne, I think meant that reading these popular science books was particularly important for me. Okay, so when I got to MIT, I really loved it there. I think of grad school as one of the really best times of my life. So here I am in my office at grad school. Here I am with Josh Tenenbaum, and so Josh is not only a really good scientist, but also a really good person. So he created this environment, it was just a good group of people. It wasn't competitive. It was just a good place to be. And some of the good people there included Andy and Lauren Schmidt, and you can see them here. And just as an example of why it was such a good place to be, here are a couple of photos from fancy dress party that Andy and Lauren organized. And people came dressed up as something related to cognitive science. So you can see Andy and Lauren here, and one of them is dressed up as Broca's area, and the other one is Wernicke's area. So sort of neuroanatomy puzzle. I'll leave it to the reader or listener to figure out which one is which. So this is a cool concept, but you need a video, which I don't have, to get the full glory of the idea, I think. And so a video might show that when Broca and Wernicke were separated, then Broca's area, without the benefit of Wernicke's area, would start talking in a way that was, you know, like Wernicke's aphasia. And poor old Wernicke, without the benefit of Broca, would start talking like someone who had Broca's aphasia. So I'm not sure if they actually, well, to what extent they actually pulled that off, but that was the concept which I thought was great. So here I am at the same event. I've probably never been one for dressing up. My costume is somewhat minimal. Here I am. So you might know the barber paradox coming from Bertrand Russell. It talks about a certain town, and in that town, the barber shaves all those who do not shave themselves. And so the question is, does the barber shave himself or not? So here I am as the half, you know, the barber with half a moustache there. Okay, so in addition to really liking the lab that I was in, I got exposed to the broader cognitive science community there, and that was exciting to me. So here's the very first cognitive science conference I went to was in 2003. It happened to be in Boston. I submitted a paper to it called Theory-Based Induction, and I was a little bit overwhelmed by the number of interesting things at that conference. It seemed like, you know, just about every single talk was something that I was interested in. So if you look at, I just randomly took the first 4 talks in the program, and I still think these are cool talks. I'd like to go and hear probably all 4 of these talks. So this was exciting to me to be able to be part of this conference, and I still think of the Cognitive Science Society as the major professional organization that's closest to my heart. In terms of research, at grad school and beyond, sort of for the past 20 years, I think that the work that I've done has fallen really into 2 main areas. And so first area, this is the area that I was working on at grad school, relates to Bayesian models of inductive reasoning. And the second area relates to language and efficient communication. And I'll give you just a glimpse of some of the things that I worked on in those 2 areas. And of course, all of this work was done in collaboration with many people, and I've only listed a couple of collaborators at the bottom here. So in grad school, a big part of what I worked on had to do with hierarchical Bayesian models, and this was all about taking hierarchical Bayesian inference, which statisticians had talked about and developed in great detail, and applying it to questions in cognitive science, which hadn't been done so much before. So to give you an example of the kind of inductive problem we applied this to, the bottom of the slide here is a little matrix showing a bunch of animals and features. So you could think about these as perceptual and behavioral features, like has a tail, has fur, moves slowly, and so on. So just by observing the world, you could learn about animals and their properties. And now I might give you an inductive problem. A new feature comes along. It might be something like having biotinic acid in the blood. So I say, okay, gorillas have biotinic acid in the blood. That's what this black square means. What about all of these other animals? The bats have biotinic acid in the blood. What about crocodiles and so on? So here's an inductive problem. It's inductive because there's not enough evidence to know for sure what the answer might be. If you had some kind of representation about similarity structure over the domain, if you knew, for example, that gorillas and bats were mammals, and mammals are different from reptiles, which are different from birds, and so on, you could use that as a basis for answering the question. You might say, well, if gorillas have it, maybe bats are more likely to have it than the other animals here. So that's good. If you had this representation of similarity, you could answer the question, but where might you get that representation from? There are different possible ways to organize animals into trees. So how might you learn which representation is the one to use? If you have observed a bunch of features already of these animals, then there's kind of the intuition, well, maybe you should go with the tree that best captures the features that you've already seen. So that kind of makes sense. And you can set up this kind of problem in terms of a hierarchy where you have tree structures at one level, features at the bottom level, and you can carry out inference on both levels. You can make inferences about new features, you can make inferences about which of these trees is best. You can even add yet another level to the hierarchy and say, well, I was showing you these trees over animals, but what if you didn't know in advance that a tree structure was a good one to capture similarity relationships between animals? What if you were entertaining the possibility that a linear relationship might be good, or a circle relationship? If you set this up in as a hierarchical Bayesian model, then you can make inferences at all 3 levels. And in particular, you can say, given the features that I'm observing down at the bottom, do I think that these elements, these animals here, are best organized into a tree, into a chain, or something else? So I suppose the result in my PhD work that I'm most proud of is this, summarized by this figure here, where we had a model and you could give it feature information at the bottom level, and it would figure out for itself what kind of representation was best. So when we gave it a matrix of animals and their features, it figured out that this tree structured representation was best. When we gave it information about Supreme Court justices and their votes, it figured out that this kind of linear representation was best, that roughly captures a spectrum from liberal to conservative. So this is what I spent a lot of time thinking about during my PhD and beyond. So if you think about induction as a problem where you're filling in missing data, I realize you can't see almost anything on this slide here, but I'm putting it up to show you that later on, together with Alan Jern, we worked on a framework trying to think about the broad set of inductive problems, put them in a taxonomy, and over, I suppose, the past 20 years or so, I've worked on a number of different inductive problems, and this paper with Alan was our attempt to kind of put it all together into one comprehensive framework. So inductive reasoning was the main thing that I was working on during my PhD. So one of the good things about PhD in the US is you have more time than you do here. And so there was time to think about other things as well. And I spent quite a bit of time thinking about social systems as well. And this was kind of a guilty pleasure, I think, at the start. I sort of thought of it as a distraction from what I was supposed to be doing. But my interest in this was sparked by a book I read on ethnomathematics. And it wasn't exactly the paper I've taken this quote from, but it talked about a similar idea. So if you look at this sentence, it's talking about André Weil, a group theorist, who wrote a mathematical appendix to a book by Levi-Strauss on kinship, talking about using group theoretic techniques to model Australian marriage systems. So this kind of blew my mind. I knew a bit about André Weil from the math training that I'd done. He was a group theorist. I knew a bit about Levi-Strauss, and I was independently interested in both of those things. So to find that the two of them came together in this appendix that was about Australian marriage systems, that was, still is kind of mind-blowing to me. So I read a lot about this. I found it really interesting. I didn't end up working directly on this at the time, but Australian marriage systems crept into a paper that I wrote, which was about relational learning. So we had a paper, and as one of the examples in that paper, we analysed a data set compiled by an anthropologist who lived with a group, the Illawarra, in the Northern Territory. And as part of the research, he took these 104 people, and for each person, he went through a set of photographs, everyone else in the community, and asked them, which word do you use to refer to this person? So it's this rich, interesting relational data set. There are 27 different kinship categories. I'm only showing you 6 of them here. And it turns out with this relational learning model we developed, the model is able to automatically organize people into groups in a way that makes, that gives the relational data here a clean block-like structure, and that makes sense given what we know independently about other aspects of the culture. So this idea about trying to understand people by looking at a computer screen, I think this was something that my family would often tease me about. You know, here you are, you say that you're interested in people and you spend all day looking at a computer. That was particularly something that came out particularly while I was doing this work, because my sister happened to be deputy coroner in the Northern Territory at the time. So here she was going around visiting different communities, actually learning about kinship for real and interacting with people. And here I was sitting behind my, computer making pictures like this. So they gave me a hard time about some of these things. Okay, so this interest in social systems led me at one stage to discover this journal called World Cultures, which was kind of ahead of its time, I think. It started in '86, and it was a journal that included floppy disks with DOS programs and data sets. So this, I think, was a pretty obscure thing. MIT didn't subscribe to this. I had to go to Harvard Library to find this. And I happened to find this data set which talked about kin term patterns from many societies across the world, more than 1,000. So this is really an amazing resource. Even documenting a single kinship system, that requires an anthropologist or a linguist to go to a part of the world, spend a number of years learning about social structure there. And here was a data set with 1,000 of these things. And I couldn't quite figure out anything to do with this at the time, but it turned out to be important later on, as I'll mention. So this, I think, is kind of a serendipitous discovery that turned out to be useful. Here am I around the time I went on the job market. So I applied to a number of, so for me, the big decision was whether to come back to Australia or stay in the US. And I ended up applying to places in the US, although I was never quite sure that was the right decision. I was fortunate to get offers from a number of good places. And some of the reasons, again, this is good fortune coming in. I happened to be working in a hot area. So at the time, Bayesian models of cognition were sort of a hot area, and it was almost as if every department maybe felt that they needed somebody doing something a little bit like that. I was also applying just before the great financial crisis hit. So had I been applying a year or two later, probably would have been a very different outcome. Another thing that served me well, I think, was my broad interest in cognitive science. So I know, for example, people at CMU told me that they were impressed by the fact that I was able to talk about vision with the vision people and talk about cognitive development with the development people and so on. So I think there was a large element of good fortune here to be able to get a job right out of grad school. And I ended up going to CMU. And one of the reasons that CMU was so appealing to me was there are people doing cognitive science, and not just any kind of cognitive science, but the part that excited me most across 5 separate departments. So just as an example of that, here are 3 books that I associate with CMU coming from 3 different departments. So John Anderson from psychology, Tom Mitchell from machine learning, and Clark Gleamore from philosophy. So the fact that there was so much interest in cognitive science there was a big draw card for me. Also, I could tell that CMU was a place where there were close-knit and supportive colleagues. And that turned out to be right. And so it was a really good environment to work in for the next 10 years. This close-knit and supportive colleagues idea, part of the reason I knew that before I actually went there was a group of academics there who had gone to lunch with each other, I think, regularly, for some of them for 20 or more years. And so they genuinely liked spending time with each other. Also, they were genuinely interested in what everybody else did. So it was a department that had developmental psychology, social psychology, and cognitive psychology. But what united all of those things was a shared interest in sort of rigorous theory and psychological mechanism. And so it was a good place to work. Here's just an example of why it was kind of a good set of colleagues to interact with. Eric Thiessen, one of the other junior people there, was the editor of this departmental magazine called the Psychological Bulletin. And he was sort of ahead of his time. He was doing fake news, back in 2005 before Donald Trump hit the scene. So I'm not sure if this is my first appearance in the Psychological Bulletin or not. If you have a look at it, well, it's completely made up, of course, but the fact that this was a department where people would make these sort of nerdy kinds of publications was something that appealed to me. Okay, there are other important people that I met during my time at CMU, and so here's Alan Jern, who is the first and only grad student for which I was sole supervisor. So working with him was a really fortunate thing for me. And here are me along with 3 very important people that I didn't know before going to CMU, my wife Hüting and our 2 children. So spending time with them is another highlight of life at CMU. In terms of work, I'm going to talk about one thing that I worked on at CMU, and this relates to language and efficient communication. And I got into this, I think, by being a little dissatisfied with the fact that in some of my work on inductive reasoning, we tested the theories by applying them to data collected in sort of artificial lab experiments, where you ask people to reason about made-up things like, whether an animal has biotinic acid in its blood. And I got a bit frustrated at working with artificial sorts of work on something that was a bit more real world. So this led me to think about named categories. So if you look at any natural language, the words in that natural language pick out certain categories, and you can ask, well, why does the language pick out the things that it does? You can look at that for kinship. So here is a little fragment of the family tree, and you can see the colors here, color-coded squares are meant to represent 2 different ways to carve that up into categories. As an English speaker, if Alice here is an English speaker, she would use the same term grandmother for her mother's mother and her father's mother. That's why they're both in the same color. If Alice grows up speaking Northern Paiute, then she would have 4 different terms for grandparents that she would need to learn. So kinship's one example of this. Color naming is a classic example of this. So here's an array with hundreds of different color chips. If you ask speakers of different languages, what labels they'd apply to all of these chips, you get very different answers. You don't get the categories that correspond directly to the color terms that we have in English. So if you ask speakers of Wobe, language from the Ivory Coast, they have 3 basic color terms, and the extent of those terms is represented by the mode map here, and you get different answers in different parts of the world. The theoretical approach that I was applying to this, along with collaborators such as Terry Rupier, was to say, well, different languages have very different systems of categories, but maybe that's because there are different ways to achieve trade-offs between the constraints that shape naming. And so we were thinking about a case where in this little picture here, each little dot is a possible system of categories. So a possible system of color categories or a possible system of kinship categories. And they're in this space which has 2 dimensions. So complexity and communicative cost. And so the idea was along this optimal frontier are all the systems that achieve efficient trade-offs between these 2 constraints. And the prediction is, if you look at languages of the world, you're going to find systems that lie along the optimal frontier here. So we were sort of thinking about these ideas, partly inspired by some things we knew from the economics literature. We didn't know at the time, but there's a very closely related branch of information theory called rate distortion theory, going back to Shannon in the 1950s. So here's a picture from his paper there, and this rate distortion curve that he's showing there is closely related to the ideas that we were kind of trying to develop without knowing the information theory angle. And it was Noga Zaslavsky later who kind of allowed us to see the connection here. So let me try to make this a little bit more concrete by talking about color naming as an example. So here are 3 possible color systems. You could imagine a system like this, which has a different word for every single one of the 300 chips in the array. So that would be high in complexity. It's very hard to learn and remember, but it would be low on the communication cost dimension, because every time you use one of those words, the hearer knows exactly what you have in mind. The other extreme, you could have just a single word for every color. So low in complexity, easy to learn and remember, but high in communication cost, meaning that for each communicative interaction, there's a high cost involved because the listener doesn't really know which color you have in mind. And along the frontier here, you get intermediate cases like the one I'm showing here. So one of the reasons that this framework was appealing to us is you can use it to explain not just what languages are like in general, but you can explain certain properties of individual languages. So I'm showing you here results from a paper by Noga Zaslavsky, and you can see in the top row here human naming systems. So these are based on experimental data. On the right here, based on English speakers. So you can see the basic color terms of English: green, blue, purple, pink, so on. The bottom layer here, you can see the systems that are theoretically optimal according to our model and that have a similar level of complexity as the human naming systems in the top row. So you can see that the model is not getting everything right. It's not getting the boundaries between the categories exactly right, but it's doing a decent job. It's giving us some insight into why these different languages might partition color space the way that they do. So as a couple of summary results, we applied this to kinship, and this was facilitated by the data set that I serendipitously discovered that I mentioned before. And we were able to show that real-world kinship systems lie along the optimal frontier. This from Noga's work showing that real-world color naming systems lie along the optimal frontier. And these ideas, I wouldn't have expected to be working on some of the applications that we ended up looking at, but these ideas have proved to be relatively general, I think. We use them to look at season naming across different cultures in the world. So here's just one result showing that for Gudwingu, which is a language spoken up in Arnhem Land, it's a language which divides the year into 6 named seasons. And so we compared the actual Gudwingu naming system to what you'd expect if you took climate data from the region and you said, oh, what's the theoretically optimal system that will kind of be most useful for communicating about a region with this climate. You can see that again, the model predictions, category boundaries are shown as these lines here. They don't exactly map onto the attested system at the top here, but it's pretty close. Most recently, and Frank Molliker took the lead on this, we applied similar ideas to grammatical marking. So no longer looking just at words, but looking at things like tense marking, how you mark past, present, and future. And again, attested systems, those are the black dots. In most cases, are falling along the optimal frontier here. Okay, so I was doing this work at CMU. I worked at CMU for around 10 years in total, and towards the end of that time, I was able to do a sabbatical in Melbourne. So I'm grateful to Dan Little, who was my host for that. And that was good as a way to interact with people here and spend time with family. And I suppose the number one thing I remember working on during that year was another thing that seemed like a guilty pleasure at the time, sort of looking at stars and grouping of stars into constellations across different cultures. And so it was kind of a guilty pleasure because, you know, it wasn't related to the grants and other things that I was supposed to be writing at the time, but I found this fascinating and I kept on working on it. And I later discovered that people here were interested in very similar things and were approaching it from angles that I hadn't thought about. And so this is a picture from a paper that we submitted and are currently revising. It's showing, here's the night sky. It's showing predictions of the groups that are best according to a model that we have. And so the model picks out Orion over here, picks out the Southern Cross over here, picks out the Big Dipper over here. It's not getting everything right, but it's doing a decent job of explaining which structures are most commonly found across cultures. At the time of starting the sabbatical, I didn't really think that it was going to be anything more than a sabbatical. You know, sometimes people have a sabbatical as a way of trialing what it might be like to move to a place. That wasn't what Yuting and I were thinking, but we liked it here and ended up moving here. And again, this was a very fortunate thing, I think, because to be able to get 2 academic jobs is not an easy thing. And again, I suppose we were able to move a couple of years before another crisis appeared and would have made it impossible to do that sort of thing. So the big reason to make the move, I think, was the people. I think Melbourne has always been strong in mathematical psychology, but a little bit before I came here for sabbatical, Simon and Andy had just started, and so there was more kind of cognitive science in addition to mathematical psychology. So it was clear it was in good environment to work in, and also the fact that my family here was a big draw card as well. As for what I've been doing here, I suppose the number one thing I've been working on is related to the work on language and efficient communication. So for the next couple of years, I'm fortunate to have a fellowship that supports my work, and this is, the quote here is from the abstract of that fellowship. So still looking at different systems of categories around the world and trying to understand this through the lens of efficient communication. If I look back at these 2 big themes, I think, that have characterized my work, in my mind, they're actually quite different. So looking at different parts of cognitive science and using different theoretical tools. So statistical models on the left here and more information theoretic ideas on the right here. And I have realized that, you know, if you look at this slide here, you might say, oh, Charles works on a given set of ideas for about 10 years and then moves to something else. So if that's right, then, you know, maybe something new is going to come up in a year or 2. But at least as from where I stand now, I think there are lots of ideas related to language and efficient communication that we haven't explored yet and that I'd like to explore. And so that's the thing that I'm most excited about working on. I do have, you might call it linguist envy or anthropologist envy from time to time, because these are the people who are able to collect the data that allows us to test these sorts of theories. So to some extent, I feel a bit like a parasite, you know, coming in over the top and using data that other people have collected and data that other people know better than I do. But, you know, maybe it's good to have a research ecosystem where people are doing different things and contributing different sorts of perspectives. Maybe one of the last ideas I wanted to mention is that recently I've been spending quite a bit of time thinking about trying to promote cognitive science around the world and build community for cognitive science around the world. So this is a map I made based on membership statistics for the Cognitive Science Society. So the society is dominated by US members, around 2,000 members, and the dots here are showing the size of the communities in different parts of the world. So I'm fortunate to be able to do this by being part of the governing board of the Cognitive Science Society. And so if people have ideas about how we can how the society could do things better to promote and support cognitive science in different parts of the world, please come and talk to me about that, because that's something that's something I'm thinking about a lot. So if I think about my story over the past 20 odd years, it's a story that's involved moving from Australia here to the other side of the world and back again. It's a story that's involved starting off as somebody feeling, probably wrongly, but this is how I felt as an undergrad. I felt that I was trying to do cognitive science on my own, but now I'm in a position where I'm able to think about trying to help the Cognitive Science Society do a better job of making cognitive science visible and something that people all around the world are able to participate in. So I think these are massive privileges that I have. Maybe as a final slide I'll put up here, there aren't that many opportunities where you're able to publicly thank all of the people that have made a big contribution to your life and your career. So this is my attempt to put at least a handful of them onto a single slide and to say thank you for the many ways in which people, including people here in the audience, have shaped my story and my journey as a cognitive scientist. So in the minutes that we have remaining, I realize this is a somewhat strange kind of talk, but if anyone has questions about either the research content or the other parts of the talk, I'd be happy to do my best to address them.
So Simon will raise his hand for people on Zoom. Other people raise your hand. Yeah, and if you can rephrase the question.
Yeah. Yeah.
I'm curious, how is artificial intelligence changing the way that you work with big data?
So the question is, how is artificial intelligence changing the way that I work with big data? So I think for me and a lot of other people, I was surprised at the success of deep networks. And if I were, I suppose, in terms of how it's changed what I actually do, along with collaborators, we do use deep networks more as a tool in certain projects. So if you have, for example, let's say you're interested in how people categorize animals and you have a big set of images of different animals, you can use the internal representations of deep networks as a pretty good way to get a similarity space. And you can use that similarity space as a basis for building psychological models of categorization and so on. So that's one way in which it's shaped. In some of my projects, we're taking that kind of approach. But I would say that in terms of the actual theoretical approach, mainly the technical ideas I work on still come from Bayesian statistics and information theory. And so they're kind of not the ideas that are directly coming out of work on deep learning. But I guess I'm following that as an interested onlooker rather than someone who's actively working in that area. Yeah, Andy.
So you told that if you had a time machine and you could go back to young undergrad Charles or young grad school Charles, what would you say to him? Like, would you have it like, you told a sort of kind of nice story and everything, and but I'm wondering, yeah, if there are bits that you wish in hindsight that you'd known, or yeah.
Yeah, well, I have a very clear message for undergraduate Charles. So, and the message would be, go and talk to some of the academics that are teaching your classes and ask if you can get involved in research in some way. So I said that I felt as if I was trying to do cognitive science on my own, but that was largely, I think, out of ignorance. There were people here and at Monash doing really interesting things, and there still are. So just as a couple of examples, there was Jeff Pressing in the department here, and as well as being an amazing person, a musician and a motor control researcher, he was sort of moonlighting as an AI researcher involved in a company called Intelligenesis that was, I don't know if it was listed on the New York Stock Exchange or whatever, but it was trying to use AI to make a system that could, you know, make good investing decisions. And so I mean, who knows what he might have said, but I would tell undergraduate Charles, go up and talk to Jeff Pressing and ask if you can, you know, learn about that or get involved with that. At Monash, there are people like Kevin Korb and Ann Nicholson doing really interesting work on Bayesian models. And in particular, I would have told undergraduate Charles, don't do your honors thesis in information retrieval at University of Melbourne, which is what I did. I would say, go and talk to Kevin Korb and do an honors thesis at Monash on something related to, you know, Bayesian philosophy of science, or maybe minimum message length, or something like that. So there were opportunities here. There are people doing amazing things. I just didn't know about them as an undergrad. My message to grad student Charles, I'm not sure that would be what that would be exactly. I sort of it's harder for me to identify things that I should have done at the time that would have made a difference. Hey, thank you.
Thank you, everyone. Next week we have Dan, and hopefully fewer technical problems. But thank you, Charles, very much for giving the first one, for having the idea actually for this kind of seminar series. It was Charles' idea, and for leading the way. So thanks. Thank you all for coming.